exponential growth and decay. If you did not do the investigation from day 6, you will want to borrow a calculator from Miss Using and work on that first. So we're going to talk about a little bit more formally those exponential equations, those ones that yesterday we saw those exponential growth or those decay equations. So this first one, if b is greater than 1, it went up. And we have all this stuff from yesterday that we'll talk about, summarize that. And then if it's in between that, so if, for example, if it was between 0 and 1, like 1/2 times, or excuse me, if our b value was 1/2, so like 3 times 1/2 to the x power. And we talked a bit about shifts yesterday as well, the left, right, up, down. So this first one we're asked to graph is y equals 4 to the x. So, and you might remember some of this from yesterday, but you know, if we have 0, anything to the 0 power is 1. When x is 1, 4 to the first is 4. So we have those equations 0, 1, those coordinates, 1, 1, 2, 3, 4. We know it hasn't shifted, so our asymptote is the x-axis, and then it shoots up. Where if we have 4 to the x plus 2, well, what happened here? It shifted up 2. So when x is 0, 4 to the 0 is 1, plus 2 is 3. When it's 1, 4 to the first is 4, plus 2 is 6. But what we have to remember is our asymptote shifted 2. So from the x-axis, it moved up 2. So we have the coordinates 0, 3, and 1, 6. Whoops, and I missed that one, but there's our graph there. Well, what about these where b is between 0 and 1? Well, we have our decrease there. So y equals 1/5 to the x power. We can make our xy table. Well, 0 is 1. Let's see, 1 is 1/5. So we have 0, 1, 1, and 1/5. So it runs along the x-axis and then increases this way. Well, what happens? What does that 6 do? Well, it's affecting the whole thing, so it's a vertical stretch. But we can make that table as well. When it's 0, let's see, it's going to be 6 instead. When it's 1, let's see, 6 times 1/5 is 6/5. So now we have 0, 6, 1, 2, 3, 4, 5, 6, and 1 and 6/5. So it's this vertical increase. So it still looks the same, but it's getting higher faster there. So exponential growth and decay, here's our equation for it. We start with our initial amount, and then it's 1 plus or minus our rate to the number of years. So if we look at this, I'm going to write that equation, n sub 0, 1 plus or minus our rate to the t. Our initial population is 500, so we start with 500. If they increase at 14%, so 14% is 0.14 to 22 weeks. And then we'd have to type that straight into our calculator. And this last one, an entomologist monitoring a grasshopper plague noticed that the area affected by grasshoppers is given by this equation, where n is the number of weeks after the original affected area. Find the area after 5 weeks, 10 weeks, and graph it. Well, the original, that would be time equals 0. So 1,000 times 2 to the 0.2 times 0. Well, we know anything to the 0 power is 1. So the original would be 1,000 grasshoppers. So if we were to graph this at 0, it would be at 1,000. So maybe we just scale it by 1,000. After 5 weeks, 1,000 to, times the 0.2 times 5. Then we're going to do 1,000 times 2. I don't know why I keep putting parentheses there. 0.2 times 10. So 0.2 times 5 is 1. So 1,000 times 2 to the first. I'm parenthesis happy here. So let's see. We have 2,000. So when it is 1, 2, 3, 4, 5 weeks, we'd have 2,000. And let's see, 0.2 times 10, well, that'd be 2, so 1,000 times 2 squared, so that'd be 4,000. So then 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, oops, 10. So it's going to start going up quickly.